Well, good morning there, students. Hope you had a great Easter. Hope you had a nice spring break. Um, Welcome to chemistry. Trying something a little bit differently here today, so hopefully I can get things worked out. Let me share my screen here. Okay, hopefully this will work for you. So it is Monday, April 13th, 2020, and we are in chemistry class, and we are starting a new chapter. So chapter 7 is going to be on ionic and metallic bonding. Our learning targets today: I can define and use vocabulary associated with ion formation. I can describe the process of ion formation. I can determine the type and charge of the ions formed by common elements. So let's review a little bit. We had a term called valence electrons. That's an extremely important term when we go into talking about our ion formation and our chemical bonding in general. So the valence electrons are the electrons in that highest occupied energy level, that outermost energy level, because those are the electrons that are involved in chemical bonding. When two atoms come together, it's those valence electrons on the outside of the atoms that are coming into contact, and how they behave relative to the atoms is going to determine if the atoms stick together and form a bond or bounce off and do their own thing. Now, there's a shortcut to finding valence electrons that I hadn't showed you before. Maybe I should have, maybe it didn't. It didn't come up yet. Okay, so when you look at your periodic table, remember our current numbering system numbers the columns just with our regular counting numbers: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. But there's the older system with the Roman numerals. If you look at the Roman numerals, the representative elements, which is the first two columns and the last 6 columns, have Roman numerals 1 through 8. The valence electrons of those elements in those columns is 1 through 8. So what I'm saying is, this first column of the periodic table, all these atoms have 1 valence electron. If you write out their electron configuration, it will end in an S subshell with 1 electron in it. If you're looking at column 2, that configuration will end with an S2 configuration. There are 2 electrons in the outermost level. These in column 3 are going to have a S2P1. So altogether there's 3 valence electrons. And it goes up to 8 valence electrons, which would be S2 and P6. Point out, some of you are recognizing already, helium obviously doesn't have 8 valence electrons. Helium is positioned here. It's one of the elements that really has kind of a, when you look at the periodic table, it fits in 2 places. By electron configuration, helium should be right over here next to hydrogen. But by chemical properties, and remember, Mendeleev, when he designed his first periodic table, really gave over to chemical properties being the most important thing. By chemical properties, helium has its valence energy level full. Its valence energy level is the first energy level. It can only hold 2 electrons. So it's full, even though it doesn't have 8. So from here on out, if I ask you to find valence electrons, if I say, how many valence electrons does iodine have? We say iodine's in group 7. It's got 7 valence electrons. It's that easy. Let's review a little bit. We didn't do much with electron dot diagrams, but it was defined. Electron dot diagrams is just a way of representing atoms, and it shows us 2 things. It has a symbol of the element, and the symbol represents the nucleus and any of the inner electrons. And then we use dots just to represent the valence electrons. So here's all the atoms in the 3rd period of the periodic table. and their valence electrons go from 1 up through 8. And so we have 1, 2, 3, 4. With those first 4 electrons, we put them singly, 1 on each side. And then with the 5th electron, we start getting pairs, pairs, until finally the noble gases, the last column of the table, have 4 pairs of electrons for 8 valence electrons. All right, so this is a statement called the octet rule. And you'll want to file this one away. Definitely it goes in your notes. Atoms tend to gain, lose, or share electrons such that they achieve 8 valence electrons. Oct means 8. Oct is a prefix for 8. That 8 valence electrons is a noble gas configuration. So as an example here, this is a representation of sodium. Sodium has 11 protons in its nucleus, some number of neutrons. Neutrons aren't involved in chemical bonding, so we're not really talking about them much. And it's got 11 electrons. And if you write them out, well, there'd be 2 electrons in the first energy level. Second energy level has a S sublevel and a P sublevel for 8 electrons. And sodium has 1 valence electron. So according to the octet rule, sodium is going to gain, lose, or share electrons so that they get to 8 valence electrons. And I hope that this makes sense to you, and you look at it and say, well, if sodium just loses that 1 electron, then its outermost level becomes the second level, which is full with 8 valence electrons. That seems like the simplest solution for sodium to get to a noble gas configuration. And in fact, that's what sodium does in our chemical reactions. It loses 1 electron. So if we apply the octet rule to atoms as you go through, let's look at like the representative elements again. These are the elements of the 3rd period. The atoms over towards the left tend to have few valence electrons. 1, 2, 3. If you have few valence electrons, you tend to lose those electrons. Now, when we come over to this side where we have 5, 6, 7 valence electrons, this basic version of Smart Notebook has this watermark here that if I'm working from home, that's going to be there. But this says tend to gain. These atoms tend to gain electrons because look, if chlorine's got 7 valence electrons, if it just gains 1 more, it would have a configuration just like argon. If chlorine were to lose electrons, well, it'd have to lose 7. So think about losing 7 or gaining 1. You know, imagine that we were in class, our classroom, and I gave you a choice of a job. Okay, you can either carry 7 desks from our room down to the East Gym lobby, or you could go down to the East Gym lobby and get 1 desk and bring it back. Well, not getting into, how much time you want to get out of class, as far as overall effort goes, I think you understand that going and getting 1 desk is easier than carrying away 7 desks, okay? So chlorine is looking to gain 1 electron as opposed to losing 7 electrons. Now, when you get to the middle here, the 4, the 5, sometimes 3s even, not so much the 3s, but the 4s and 5s, and to some extent it extends up into these. There is also the sharing portion. Sometimes atoms share electrons with each other. Now, in the chapter that we're doing right now, we're focusing on the loser gain. The next chapter of our textbook is going to talk about the sharing of electrons. All right, what's next? So let's get into this idea of ion formation. Definition: an ion is a charged particle that results from gaining or losing electrons. Make sure you have that down in your notes. If you have to pause the video, do it. A charged particle that results from gaining or losing electrons. So we have two different types of ions. We have cations. Cations are positive ions that result from losing electrons. So we do all sorts of weird things to try to help us remember. So I'm saying cation, think about all the funny cat videos that you've ever seen online, and you got to be positive about those silly cats. Even when the cats are being jerks sometimes. So I drew my little kitty cat face with the positive sign representing its nose. Okay, that's just a visual to help me remember that cations are positive. Doesn't have to make any sense to you. It just has to help you remember. So what makes cations? Metals. Metals tend to lose electrons to form cations because metals typically have only 1, 2, or sometimes 3 valence electrons. So the process. I'm basically here trying to pull out every way I can think of to show you this process, all the different notations. So here's a representation of a sodium atom showing rings representing the different energy levels. Okay, and sodium has 2 electrons in the first and 8 electrons in the second and 1 electron in the third. So if that sodium atom loses, oops, that's not what I wanted to do. Okay, I'll just do this. Imagine that electron gets lost. Now sodium is going to be, well, think about it. It's going to have still 11 protons in its nucleus, but if it loses that electron, it's only going to have 10 electrons. And if you add that up, that's a net of 1 positive. Sodium ends up with a positive charge. So a sodium atom becomes a sodium ion. Up here, I have an electron dot notation, sodium with 1 dot. Well, let's imagine that sodium loses that 1 dot. Here's an electron configuration for sodium. 1s2, 2s2, 2p6, 3s1. Let's imagine that sodium loses that last electron. Here's orbital notation showing how all the electrons are distributed in orbitals for sodium. And this last electron is in the 3s. Let's imagine we get rid of that. Okay? All those are going to result in a sodium ion. Okay? And sodium ion is either written Na plus or Na1 plus. Sorry, this was covered up a little bit by the watermark. So Na plus or Na1 plus. Now, you might see me somewhere along the way, going way back to my school days, I got in the habit of writing the charge in front of the number, and that's not the accepted way of doing it. And so if I do that once in a while and I slip, forgive me. You can politely correct me on it. But the ways of doing it are either to just put pluses or put a magnitude 1 with the plus, something like that. All right, I think this right here is the same stuff. Oh, so if we start out with a sodium atom, we end up with a sodium ion. In this case, because it's a positive ion, it's a sodium cation. Here's a calcium atom. Calcium has 20 electrons altogether, but calcium has 2 valence electrons. So in its outermost level, those 2 electrons. So what's it going to do? Well, calcium is going to tend to lose those 2 electrons. So we would write calcium ion. We have a calcium atom, but now we form a calcium ion, and you would write it with calcium and then superscript 2 pluses, or you would just say 2 plus. And once in a while, I might forget and slip in and write +2. This is, I mean, I wouldn't mark it wrong on your test either, but try to get in the habit of using the correct systems. All right. What if we have a transition element? So zinc is a transition element. And if you write out the configuration of zinc, we got all this, 4s2, 3d10. So even though our Aufbau principle says that the 3d is the last electrons that we fill in, the fourth energy level is the highest energy level. That's our valence electrons. And there are 2 valence electrons. And so zinc tends to lose those 2 electrons. So the zinc 2 plus ion has that same configuration with the 4s gone. Okay? Now this is called a pseudo noble gas configuration. And I kind of hope that you know from other language use that pseudo means false. If you don't, well, now you do. Pseudo means false. So it's got not only its 8 normal electrons in the S and P sublevel, it also has D electrons, but in this case, the D sublevel is also full. And that's a pretty good electron configuration. Okay, so zinc would like to do this. It would like to lose those 2 electrons. Transition metals usually have 2 electrons, 2 valence electrons, because the S sublevel in front of its last electrons, it has 2 electrons, and it tends to lose those. Okay, it's very common for those to lose 2 electrons. Now, sometimes elements do more than one possible ion. So let's just take a look, and I'd recommend that you actually draw out an electron configuration for iron. Iron has 26 electrons. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. So the valence electrons are the 4s2. So based on what we just said, it would be expected for iron to probably lose those 2 electrons. So here I rewrote it with those 2 electrons gone. That would be a +2 ion. And iron does that. Iron forms compounds where the atoms have lost 2 electrons. But iron also forms compounds where it's lost 3 electrons. How do you explain that one? Well, look when you write that out. If you take 1 more electron away, well, we'll take it from the end. And we end up with a 3d5. D5. That's a half-filled D sublevel, which, remember, a half-filled sublevel is pretty good for stability. And it turns out, in iron's case, that the Fe3 plus is actually the more common ion. So iron sometimes, you know, if I just have a piece of iron, a nail or something, that's neutral iron. That would have this configuration. But then in compounds, sometimes iron gives up 2 electrons, or sometimes it gives up 3 electrons. Copper. You remember that copper was one of our exceptions to the octet rule? I'm sorry, not to the octet rule, to the Aufbau principle, the diagonal rule. Instead of ending up 4s2, 3d9, it ends up 4s1, 3d10. And so we have this single electron in the S sublevel. And if we lose that, we end up with copper 1. Now, copper also quite commonly loses 2 electrons. And to explain the 2 electrons, I guess I'd have to go back to saying, what if we imagine the regular Aufbau principle where it would have had 4s2, 3d9, and then it would lose those 2 s electrons and end up like this. So I can't explain to you. I don't understand it myself. I haven't researched this. All the subtle little nuances of the energies of electrons. But apparently, this last one is a better fit because copper-2 compounds are more common than copper-1 compounds. Copper actually does this more often than this one. I would want you to be able to associate, if I give you a charge of one of these ions, can you tell me how the electrons would still be arranged? So you should be able to, you know, that copper, yes, it would want to lose one electron, but if it loses a second electron, where would you take it from? Well, you take it from the end, the last. You should be able to handle that. So let's talk about anions a little bit. Anions are going to be opposite, so you can think of anion, a negative ion. They're negative ions formed when atoms gain electrons. And who does that? Well, nonmetals do that. Nonmetals tend to have quite a few valence electrons, and they tend to gain electrons to fill up their valence energy level. Now, the name changes. When an atom forms an anion, we change its name to end in the letters IDE. So think about it. You've heard some of these things. You know that we have the element chlorine, but you've all heard of chloride. Oh, chloride is just the ionic form of chlorine. Fluorine becomes fluoride. Bromine becomes bromide. Iodine becomes iodide. Oxygen becomes oxide. Sulfur becomes sulfide. They change their name. All right, so here's that sulfur. Sulfur has 6 valence electrons. So what's it want to do? It would like to grab 2 electrons from somewhere else. And if it grabs 2 electrons, you fill up that valence energy level. So now it's got 2 extra electrons. Think about it. It's got 16 protons. It had 16 electrons. Now it's got 18 electrons. And so its overall charge, 2 extra electrons. So we now call it a sulfide ion. We say S2-. The charges are always written as superscripts. If I were looking at an electron configuration, it would have normally ended up 3p4, but now we have to change that to 3p6. The last sublevel would have had 4 electrons in it, but we fill in 2 more arrows. That's anion formation. Okay, same thing, dealing with sulfur. And here's one more example. Phosphorus. Phosphorus has 5 valence electrons, so imagine phosphorus grabbing hold of 1, 2, 3 more electrons to fill up its outer level. So instead of ending up 3p3, it ends up 3p6. Instead of 5 dots, we now have 8 dots. Phosphide anion. So that's it for today. I'm going to stop my screen share here. So you're going to have an assignment from the book to go with this. Make sure that you are filling in some things in your notes. I don't think this is going to take terribly long for you to do today. I think ionic bonding tends to be fairly straightforward for students. This is actually going to be a very, very short chapter. It's only going to take us a couple of days to do this. Prepare yourself for that. Hope that you're having a good time. And as always, if you need help, please, please, please contact me. I can sit down and do a Zoom conference with you. I can talk to you over the phone. The one thing that doesn't work the best for me is to type back and forth in email or text. Not if we're trying to actually discuss something, okay? I don't type very good, so it takes me a long time that way, where I could just try to explain things, and I can set up cameras that I can show you I can write out on a piece of paper and explain while I'm going. I've had some success with other students that way. So if you need help, please let me know. Okay. Stay safe out there. See you tomorrow.